Hi there. In this video we're going to start chapter 3 and we're going to look at some applications of derivatives that are different than the ones we've seen. So we're going to jump right in with maximum and minimum values. So we're going to start with the definition of an absolute maximum and minimum. These are sometimes called global maximum or minimum. And the idea is that an absolute maximum is the highest point on its graph. So everywhere on the domain, look for the highest y-coordinate. That's your absolute maximum. So you can see here, the maximum here is 2. And it occurs at x equals 2. So the maximum is y equals 2. And if we talk about the x-coordinate, then you have to list that as well. And then the absolute minimum is just the lowest point on its graph, which has a y-coordinate of -2, and that occurs at x equals 0. These are pretty simple. It's pretty much what you see is what you get. One thing to remember is that the definition includes a less than or equal to, which means you can have multiple cases. You could have, 2 or more of the same y-coordinate, and they're all considered individual maximum values. Even though they're the same number, they happen at different spots. All right, so the next thing we're going to look at is something called a local maximum and minimum. And the idea here is that if you look a small distance on either side of the point, a local maximum is the highest number, the highest y-coordinate, in that small window on either side, like here. And it doesn't really matter how far you go out. If you can go out some distance, just any amount, it's a local maximum. Local minimum, same sort of thing. Right? Just got to be able to go a small distance on either side in the x-coordinates. These definitions do not require continuity. We will see that in a little bit. Okay, over here you can see this is a local minimum. It's also an absolute minimum. It's the lowest point overall on its graph. And it's the lowest point in that small region around the point. Again, we list these things the same way. List the y value as your minimums and maximums, and you may be asked to identify the x-coordinate as well. On the homework, sometimes you have to list the x-coordinate, sometimes you don't. On an exam, I will always require you to list the x-coordinate. So one thing to keep in mind when we're trying to identify maximum and minimum values is where can these things happen? Are there restrictions where you can have maximum and minimum values? So according to our definition, we have to be able to look on both sides of x equals c. So it has to go, the function has to exist on both sides of the point. Because of that, it's a logical consequence that endpoints cannot be local maximums and minimums. Endpoints can be absolute maximum or minimum, but not local. And to simplify the language, sometimes we call any maximum and minimum y values are just called extreme values, whether they're local or absolute. And the points themselves, so the x-coordinates and the y-coordinates together, whether they're local or absolute, are just called extrema. I know it's a lot of terminology. Just get the hang of it. There's lots of practice on the homework, lots of practice with the problems in the book and the exercises at the end of the chapter. So let's jump right in and do one of these. So local maximum values. So you just look for any point that's the highest in a small region on either side. Well, that's going to be 1, 5 right here, right? So the value itself, if we're just looking for the value, it's 5. If we're looking for the point, it's 1, 5, or f of 1 equals 5. This is definitely the highest point as you move away on either side. What about local minimum values? Well, we have one here, right at 0, 0, it's the lowest on either side. And down here at 3, -27 is the lowest on either side. Now let's look at absolute maximum. That's just the highest point on the graph. So it's 37 or -137. And the absolute minimum is this point again. So some points can be both. Some points can only be one or the other, just depending on where they are on the graph. So the question we want to answer at the bottom here is, does every function have both maximum and minimum values? So let's look at a couple examples. Here's the solutions for the first example. But I already went over them, but they're in the notes if you need them. So, talking about maximum or minimum values, the first graph there, x squared has a minimum but no maximum, and y equals x cubed has no minimum and no maximum. So we can see that there's different kinds of graphs in terms of where a minimum or maximum might be. We're interested in finding out where they could be. Hold on one sec. So let's look here for local and global extrema. So here's a nice graph, kind of a funny graph. And local extrema, that means local minimum, local maximum. So let's start with local maximum. You can see this point here is the highest point in its little region on either side. And that's 1, 2, 3, 1, 2, 3, 4. So that's the point 3, 4. And then there's another one over here. So that's the point 1, 2, 3, 4, 5, 6, 3. So this is the point 6, 3. So those are local maximum values. What about local minimum values? Well, you can see clearly that this one is definitely the lowest one in its small region on either side. So the point 4, 1. Any other local minimums? Well, this point might be 1. And so just think to yourself, does it satisfy the definition? Is the function around this point higher than that point? So here's the function around the point. We're only concerned with the x values. We don't need continuity. We don't need differentiability. We don't even care if it's a removable discontinuity, a jump. We don't care. So it turns out this is another local minimum, right here at 2, 2. So 2, 2 and 4, 1 are both local minimum values. So I know all of Chapter 2, we spent a lot of time using continuity to do stuff, and we will come back and use continuity to do things in the future. But for right now, we're still building up some new ideas that we're going to use in this section and the next one. So minimum and maximum are not based on continuity. They're just based on the y values themselves. All right, what about the absolute maximum? What's the highest point on this graph? Well, you look up here and you think maybe you want it to be this point. It'd be nice if it were this point. But this is an open circle, which means the function is not defined at this point. And because of properties of the real numbers, there is no number next to the point 0, 5, right? There's no next point. So you can pick a number close to 5, like 4.9, but there's a number closer, right? 4.99 is closer. And then there's another number that's closer than that, 4.999. And you might just think, well, can't I just put 4.999 repeating? No, you can't, because that's 5. So there is no maximum in this problem. No global maximum, right? No absolute maximum. Because there are no real numbers that sit next to any other real numbers. There's an infinite number of real numbers between any two real numbers on the number line. All right. What do we got next? Absolute minimum or global minimum is this point 4, 1 again, right? So if you guys are doing these problems on the homework and they're giving you trouble, contact me. I can explain it better. Students do get mixed up by properties of the real numbers. So that is something that we can talk about whenever you want. Next up is a theorem called the extreme value theorem. And it basically says if your function is continuous on a closed interval, so there will be no vertical asymptotes, then f attains an absolute maximum value f of c and an absolute minimum value f of d for some numbers c and d in AB. So the three pictures at the bottom there kind of show you why it's believable that this is true. We cannot prove this theorem. I could prove it, but it's really, really difficult, and it requires some advanced stuff that we don't get into. So think of it like the intermediate value theorem, like we saw in chapter 2. It's a similar version, right? It's basically saying that if you have a function connected at two endpoints and it's continuous, that only one of two things can happen. The function either increases and comes back down, or decreases and comes back up, in which case, if it goes up and comes down, then the top part is the maximum. And if it goes down and comes back up, the bottom part is the maximum. The other thing a function can do is just always increase or always decrease. If that happens, then the endpoints are the absolute maximum or absolute minimum. So that's basically what we're getting at here, is no matter what shape the graph has, if it changes direction at any point, then the place it changes direction is the maximum or minimum. And if it doesn't change direction, then the absolute maximum or minimum is at the end point. And that should be believable just based on what you're seeing here. Here are two things that look like counterexamples for the extreme value theorem, but they're not, because in the first graph, the function is not continuous, even though it's on a closed interval. In the second example, we have a vertical asymptote for one of the for what would be one of the endpoints, so it's an open interval. So function has to be continuous, has to be on a closed interval. If not, we can't use this theorem. Next up is Fermat's theorem. This is a really old theorem from the 1600s. And basically what it's saying is that if a function has a local maximum or local minimum at a point, let's call it C, and if the derivative exists, then the derivative has to be 0. So the picture shows you basically everything you need to know, right? So here we have a local maximum. The function is continuous. The derivative exists, right? Remember, if the derivative exists, that's also telling us the function is continuous. So we don't need to check continuity as a separate thing. So derivative exists, local maximum, therefore derivative 0. Here, derivative exists, local minimum, therefore derivative 0. That's what this is saying. What about over here? What's going on with this corner? Well, the idea is we want to know, can a local maximum or local minimum exist at a point where the derivative does not exist? And it looks like that's a clear yes, right? This is a local maximum. The derivative does not exist, but that's okay. As long as the function is continuous, you can still have a local maximum there. So Fermat's theorem isn't really talking about stuff that looks like this. It's talking about stuff that looks like this or this. So we're going to prove Fermat's theorem. It's kind of a long proof. Make sure you follow along, because you need to use this theorem to do work later on in this section and the next one. And on an exam, I can have you use this theorem. So make sure you understand the proof. Here we go. So we have a function. It has a local maximum, and the derivative exists at some point. So remember, derivative exists means continuous. So we're just using the definition of local maximum here, right? We're saying if x is close to that point, then the function is less than that value, the y value, everywhere else close to. So just in a local region. So what we're going to do is we're going to get rid of x. We're going to replace it by c plus h. So x is just any number close to c. So we're just going to call x c plus h. So h is just some small number. This is how we did it when we defined derivatives, right? It's basically the same thing we did when we defined derivatives. Then we're going to, so we replace x with c plus h, and we subtract f of c from both sides. So this turns into this. Now, because h is a small number, we can divide both sides by h. And we're going to look at what happens if h is positive first. So if h is positive, we divide both sides by h to get this expression. Now we're going to tack on a limit, but we're going to take the limit from the right. So, to visualize what's going on here, we have a local maximum. That highest point, we're moving to the right a little bit, and we're looking at, as h gets smaller and x gets closer to c, what happens to the derivative. So we're just looking at positive values of h here, right? H on the positive side. We could look at h on the negative side, but we have to treat that as a separate case, because if h is negative, we have to flip this inequality around. And we don't want to do that right now. We're going to do that in a second. We just don't want to do it right now. So here we have a limit from the left side, a limit from the right side as h gets closer to c, and here we have 0. So you can just evaluate this. This left side is the derivative f prime of c from the right. So the key to this thing is that because the derivative is a limit, that means the limit from the right and the left are the same, even if h is negative. Okay, so because the derivative exists, the limits are the same from both sides, and that tells us that whether we come in from the right or the left, it doesn't make any difference. Those limits are equal. So this is just the derivative, and that equals this. This over here equals this, and this is a less than. So this turns into f prime of c. The less than or equal to stays the same, and this is just 0. So this tells us if you come in from the right, the derivative must be negative or 0. And that should make sense. Think about the graph of a local maximum where the derivative exists at f prime of c, or just think about what it looks like. Those slopes might be 0 if it's flat, but they have to slope down and to the right if you're moving to the right of a local maximum. What we're going to do now is look at the other case. So that thing at the bottom is equation 1. The derivative, the thing at the bottom, the derivative has to be negative or 0. Now what happens if h is negative? What happens if we come in from the left side of this local maximum? So we divide both sides of our equation. So this is the equation we developed on the previous slide. Divide by h, but this time because h is negative, we have to flip the sign on the inequality. Anytime you divide by a negative number in an inequality, all the signs flip. Oops. Now we take the limit, so we're on the left side of the local maximum, take the limit from the left. So this is our derivative from the left. We can see the exact same thing is going to happen as what we had in the previous slide. Because this derivative exists, we can replace the negative with just the limit as h goes to 0, because the limit's the same on both sides, because we know the derivative exists. Those limits have to be equal. This becomes 0. Well, that tells us that the derivative has to be greater than or equal to 0. So on the previous slide, coming in from the right, the derivative has to be negative or 0. Here, coming in from the left, the derivative has to be positive or 0. So that means the derivative is 0, right? If it's less than or equal to 0 and greater than or equal to 0, the only way to satisfy both of those is that the derivative is 0, and that proves our theorem. So we will use Fermat's theorem in the future. So it's a good proof. You guys should check it out. Make sure you understand it. It requires very little geometry. It's all algebra and properties of limits. So now we're going to look at when we can and can't use Fermat's theorem, right? So if you go back to the explanation of Fermat's theorem, you saw that graph that showed you, pretty much what we're going to be using it for. Can we use Fermat's theorem to look at stuff like this? So here we have y equals x cubed. Notice the derivative exists everywhere. Check. And the derivative at 0 is 0. But there's no minimum or maximum. So we want to know, does this contradict Fermat's theorem? Well, we just proved that Fermat's theorem was true. Like I just proved it. So that means there must be something wrong with the construction of this example. Fermat's theorem says if there's a local minimum or a maximum, then other stuff happens. There's no local minimum or maximum here, so we can't even use Fermat's theorem. It doesn't apply, regardless of everything else. Fermat's theorem has two ifs. If there's a local minimum or maximum. If that's false, we can't use it. If one of the ifs is false. Okay, here's a second example. So the first if for Fermat's theorem is satisfied. There is a local minimum. Is the second if satisfied? What is the second if on Fermat's theorem? Well, the second if is that the derivative must exist at that local minimum or maximum. Here, the local minimum is at 0, but the derivative does not exist at 0. Because our second if statement isn't satisfied, we can't use Fermat's theorem here. It does not contradict Fermat's theorem, we just can't use it. Okay, so remember, the time you would use this thing is when your graph looks like it did on the slide containing the explanation of the theorem. You need to have local min or max or both, and derivatives exist everywhere at those points. Okay, next up, we're going to define something called a critical number. So critical numbers are used absolutely all the time in calculus. And basically a critical number or a critical point, we use them sort of interchangeably. So C has to be in the domain of F, and either one of the following has to be true. F prime of C equals 0, or F prime of C does not exist. So if a function is continuous, the only places it can change direction are when the derivative is 0 or the derivative does not exist, it turns out, if the point is in the domain. Because functions can change direction with vertical asymptotes, but this is telling us we can't use vertical asymptotes, right? Because vertical asymptotes are not in the domain of the function. So what we're going to do is we're going to look at what happens when the derivative is 0 or does not exist. Does anything interesting happen, right? So let's see. Let's jump right in and do this example. So determine all the critical numbers for the functions below on their intervals. It's important that you pay attention to the intervals that are given. Okay? Because trig functions are periodic, right? So trig functions, once we start getting into these applications, the domain is normally restricted, so you don't have to list like millions of points, right? All right, so let's do part 1 here. So part A. So we have this function, and we want to know where's the derivative 0 and where does the derivative fail to exist. So set the derivative equal to 0. So we're just going to do that first, right? We're going to set it equal to 0 first. Factor out fractions in the largest negative power of t. Whenever you have a negative exponents, this happens a lot, you'll see some negative exponents and some constants. Pull out all the fractions, pull out all the negative exponents, right? Look for the biggest negative exponent and just factor it out. The reason for that is that we want this expression to be easy to solve. And I'd say 2 plus t is pretty easy to solve. So this tells us either this thing is equal to 0 or this thing. So we've taken our derivative and factored it and set it equal to 0. It doesn't matter what order you do it in. It's just usually to solve the equal to 0 part first. So either this is 0 or this is. Well, this can't be 0. It's not allowed to be 0. If you graph this function, it never hits the x-axis. It's never 0. Here, t equals minus 2 makes this equal to 0. So t equals minus 2 is our critical number. Now we have to check where this whole expression does not exist. Well, 2 plus t exists everywhere. That's a polynomial. What about here? Well, it turns out this expression is undefined when t is 0, right? Because that t is in a denominator. That cube root of t is in a denominator. So that means t equals 0 is also a critical number. So the way you would do this on the homework is just to list both critical numbers. Follow the directions. It may ask you to type like t equals, or it may just say list the values, in which case you'd list them from left to right. So you would type -2, 0. Just follow the instructions on the homework. On a test, I want it to look exactly like this, of course, just like all the other questions that I've put on exams. So, not too bad, right? This one's not too bad. And you can check your answer by graphing. So graph the function and look what you get. T equals -2 is a horizontal tangent, local maximum. T equals 0 is a corner. Some people call it a cusp. To me, there's really no difference between those two things. Right? It's essentially, you know, a point of some kind. And you can see that the derivative fails to exist there, but the function is continuous there, right? So that's the only places we're going to get local maximum or minimum values, is at one of these two on a closed interval. All right, let's look at B. So here we have our function 4x minus tangent x. We're going to do the same thing we did before. Just going to set the derivative equal to 0, factor it, and then solve it. So similar situation. So we have to solve. So either 2 plus secant x is 0 or 2 minus secant x is 0. So it doesn't matter what order you solve them in. Let's start over here, I guess. So 2 plus secant x equals 0 is the same as secant x is -2. You guys might not be real well versed in secant x, but you know about cosine, so that means cosine of x is -1/2, which tells us x is 2 pi over 3 or 4 pi over 3. So we found two horizontal tangents, right? We set it equal to 0 and factored. Now we have to go over here and look at the other part. So here secant x is 2, which means cosine x is 1/2. And so we get pi over 3 and 5 pi over 3. So these are critical numbers. But have we found all the critical numbers? So what we have to do is we have to take our derivatives and set them equal to, we don't have to set them equal to 0. We have to look at where the derivatives might not exist. Okay, so we check where the derivative is undefined, or DNE. We look at the factored form of the derivative and solve for undefined values. So we're really going to do it the same way, right? So here's our y prime. I just took the factored version from the other slide. It's easier if you factor it first. Believe me on this, okay? If you look at example A, that is a very difficult thing to do without factoring it. We're trying to like minimize the amount of heavy-duty algebra work we have to do, because algebra gives people trouble. So secant x is undefined where cosine of x is 0, right? Because secant x is 1 over cosine. You can't divide by 0. So where is cosine of x equal to 0? Pi over 2 and 3 pi over 2. So are these critical values? They're not. So you might be tempted to put them in as critical values. But what you have to notice is that these were never in the domain of the original function to begin with. Right? Because tangent x has vertical asymptotes at pi over 2 and the period of pi over 2. So pi over 2 plus pi n. So those two numbers were not even in the original domain. So they are not critical values. So you have to double check this. That means the critical numbers are the numbers we got in part A. Okay, so there's a lot going on here. You have to be good at trig. You have to be able to check where things are undefined. You have to be able to solve equations where things are equal to 0. Might be trig, might be polynomials, could be rational functions, could be algebraic functions. All kinds of stuff can happen. And of course, as you can imagine, later on in the class, we're going to throw in logarithms and exponential functions, and you'll have to do it for those as well. All right, so that's 4b. And you can see from the graph that that makes sense, right? We have 4 spots where there are horizontal tangents, right? Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And we have vertical asymptotes at pi over 2 and 3 pi over 2, which are not critical values because they're not in the domain. But the horizontal tangents are critical values. That brings us to finding absolute extrema. So now we're going to use all of the tools we've been developing in this slideshow. And we're going to use the extreme value theorem and Fermat's theorem. And we're going to use these two things together to find the absolute extrema of a continuous function. Has to be continuous. It has to be on a closed interval. So extreme value theorem requires those. Fermat's theorem is going to tell us what we can do with those things. First thing you do, find the values of f at the critical numbers of f in the open interval AB. Then you find the values of f at the endpoints of the interval. So you might be wondering, why isn't this a closed interval? Well, remember, critical numbers are either where the derivative is 0 or the derivative does not exist. The derivative automatically does not exist at an endpoint because you can't take the limit from both sides. So we're excluding the endpoints as a separate calculation because derivatives will always be undefined at endpoints. So we're sort of looking at all the numbers in between the endpoints here, and then we look at the endpoints separately, no matter what. So we compute all these numbers, compute all these numbers. You pick the largest in here, that's your absolute maximum. Look for the smallest y-coordinate, that's your absolute minimum. And that's it. That's what we're going to do. So let's find the absolute extrema for the function and intervals below. So here I just did the same function twice just to make some of the arithmetic easy, so that the slideshow is not an hour long, because it's a long section. And the next one's long too. All I did was pick two different intervals. So most of the work is done in part A, and then I'll just show you what changes when we get to part B. So notice two different intervals. All right, so first thing we do is find the critical values. This is a polynomial, so the critical values will only be horizontal tangents. We won't have any divide by 0 stuff. But same thing, right? Set derivative equal to 0, factor, solve. That is the steps. Anytime you do any of these problems, follow those steps. So we have x equals 1 and -3 are both critical numbers. And notice we have to double check that both of those numbers are in the interval. If they're not in the interval, they're not critical numbers. Okay, so remember that. Now, on a closed interval, which we have, -6, 4, the absolute extrema for the function must occur either at critical points or at endpoints. So we check the y values of all critical numbers and endpoints. So we just make a table. So here I put in both endpoints and both critical points. The x values are given, right? We know x equals 1 is a critical point, -3 is a critical point, -6 is an endpoint, and 4 is an endpoint. And just compute the y value. Just plug everything into your original function. I did everything, where's my calculator? Here it is. I did everything on here. In fact, it's probably still in here. It's for the next problem. Yeah, but I just typed everything into the function grapher and used the table and just typed in -6, -3, 1, 4. Boom, there's your answers. Look for the biggest number and the smallest number, and that's your absolute max and min. So, not real tough. You just got to be really organized and be able to do some algebra and a little bit of calculus. And then draw a graph, check your answer. Yep, this is definitely the smallest value over here. This is definitely the largest value here. Right? So both endpoints contained our smallest and largest values. Right? That makes sense. Right? Sorry, I got a sensitive mouse here. All right, let's look at part B. So same function, same thing. We already got it to here in part A, right? And we already know what the critical number should be, but x equals -3 is the only critical number because now x equals 1 is not in our restricted interval for part B. So we only have to check 3 numbers. Right, now we check -6, -3, but now we have a new endpoint, which is 0. Right? Oh, that's a typo. This should say 0 right here. It's right. It's correct. It's f of 0 equals 5, but that should be 0. Right? And this time we have the same minimum, But we have a new maximum value because the function is restricted. And that's it. So all of that work we did, with extreme value theorem and Fermat's theorem, this is what we use it for. A continuous function on a closed interval. How do we find the maximum and minimum values using just algebra? Now we can use the graph to check our answers, right? And you can see -6 is of course the lowest value again, and this time -3 is the highest value. Well, that's it for today's video. You guys can check out all these extra resources. There's lots that you guys can practice. If you have any questions, as normal, post something on the discussion forum or shoot me an email. And that's it for today, and I'll see you guys next video. Bye-bye now.